Now that you've done some work on congruence and hopefully gotten some understanding about congruence classes, we're going to go ahead and prove some of those properties that we worked on in those activities. So we're going to state a theorem, first of all, that summarizes all the properties that you looked at in the in-class activities, and then we're going to give a proof. All right, so here are some of the questions about equivalence classes that you wrestled with in your in-class activities. First of all, if you have two congruence classes that are represented by different integers, how can you tell whether or not they're the same equivalence class? Is it possible for an integer to be part of two different congruence classes? And are there any integers that are not part of any congruence classes? So here's what the theorem is going to look like. As before, we're going to let n be a natural number. We're going to let a and b be integers. And we're going to define bracket a to be the set of all integers x such that x is congruent to a mod n. In other words, all the numbers that are on the same team as a. So first of all, we're going to prove, this one's not going to be too rough, that bracket a sub n is going to be equal to all integers x such that x equals a plus kn for some integer k. That'll make things a little bit easier to deal with in the other parts of this theorem. We're going to prove that if you have a congruence class represented by A and another congruence class represented by B, those two congruence classes are equal precisely when A is congruent to B mod n. Which makes sense in terms of our team model, right? If you have two teams that are the same, that means their representatives must be on the same teams themselves. If you have two congruence classes that are not equal, so bracket A is not equal to bracket B, then the intersection of bracket A and bracket B is empty. And that tells us that there cannot be any integers that are in two different congruence classes. No integers that are on two different teams. And then finally, if you take the union of all the congruence classes represented by 0 through n minus 1, you get exactly the set of integers. So let's go ahead and get started. We'll start with number 1. So number 1 is just directly applying the definition of congruence. X is congruent to a mod n means exactly the same thing as x equals a plus kn. So part 1 is not saying anything different than the original definition of bracket a sub n. So I'm not going to say any more about that. For part 2, let's see, it's an if and only if. So we're going to first assume that the two congruence classes are equal. Then we're going to show that A is congruent to B mod n. All right, so how do we do that? Well, it's going to take a little bit of logical trickery. First, we're going to make the very uninteresting observation that B is congruent to B mod n. But that is important because that tells us that B is in bracket B sub n. I mean, team-wise, it makes sense that B should be on its own team, but we need to use the definition to verify that. But now, since B is in bracket B, and since bracket B is equal to bracket A, that means that B has to be in bracket A as well. It's literally the same set as bracket B, and we just showed that B is in bracket B. But what does it mean to be in bracket A? Well, it means that A is congruent to B mod n. That's literally what it means, right? And that is exactly what we were trying to prove. So now we're going to go the other way around, and we're going to assume that A is congruent to B mod n, and then we're going to show that bracket A sub n is equal to bracket B sub n. Now we're trying to prove that two sets are equal, and if you think back to your Math 210 days, what that means is we need to prove both the bracket A is a subset of bracket B, and bracket B is a subset of bracket A. So we have two proofs, right? We got to prove that each of those sets is a subset of the other. So for the first one, we assume that X is in bracket A. What does that mean? Well, and we're going to show that X is in bracket B. Now, what does it mean for X to be in bracket A? Well, we're assuming that A is congruent to B mod n. First of all, we're going to write out what that means. It means that A is equal to B plus Kn for some integer k. Now we're going to get to where x is an element of bracket A. What does that mean? Well, it means that x is equal to A plus, we'll call it Mn, for some integer m. And now we're just going to put those two pieces together, right? The first equation gives us an expression for A. The second equation has A in it. So we're going to take the first equation version of A, plug that into the second equation, see what we get. So we have x equals a plus mn. Remember that a is equal to b plus kn. We're going to isolate that b and factor out an n from the other two terms to get b plus k plus m times n. Of course, k plus m is an integer. Both k and m are integers. And that means that x is congruent to b mod n. That's the definition of congruence. And that tells us that x is in bracket b, which is exactly what we wanted to prove. So now we're going to go in the other direction, and it's going to be very similar, but we're going to assume x is in bracket b and show that it's in bracket a. So we know that a is congruent to b mod n. That's our assumption. That's our global assumption. And so that means that a is equal to b plus k times n, where k is an integer. And what we want to do for this one, and you'll see why in a little bit, we actually want to solve for b in this one because we want to look at from the perspective of b. So that's just subtracting kn from both sides. So we get b equals a minus kn. Since x is in bracket b, that's what we're assuming. That means that x is equal to b plus mn, where m is some integer. But now we're kind of in the same situation as before. We have an expression for b in one equation. We have b showing up in the other equation, so we can make a substitution. So we're going to put those two together to get, remember, x is equal to b plus mn. We had an expression for b, which was a minus kn. We're going to isolate a, move everything else over, and factor out an n. And so we get a plus negative k plus m times n. Clearly, negative k plus m is an integer because k and m are both integers. And that tells us, by the definition of congruence, that x is congruent to a mod n. But that's exactly what it means for x to be in bracket a, which is exactly what we wanted to prove. All right, so that takes care of 2. Now we're going to prove number 3. And on that one, we are assuming, if we take it at face value and look at what a direct proof would look like, we would be assuming that the two sets are not equal, and we're going to show that the intersection of the sets is empty. Now, it's very difficult to directly prove that a particular set is empty. So what we're going to do is we're going to use the contrapositive. And the nice thing about that is we get to assume that the intersection of the two congruence classes is non-empty, which is nice because that means there's something in it. And we're going to show that the two congruence classes are equal. All right, so we know the intersection of those two congruence classes is non-empty, and what that means is there's some element that's in both of them, right? That means x is in bracket a, which by definition means that x is equal to a plus kn for some integer k. It also means that x is in bracket b, which by definition means that x is equal to b plus mn for some integer m. Now we have two expressions for x. The nice thing about having two expressions for the same quantity is that those two expressions have to be equal to each other. So a plus kn is equal to b plus mn. We're going to move that kn over to the other side by subtracting kn from both sides of the equation. And then we get a, and we're going to do some simplification too, but it's pretty easy to see that a is equal to b plus m minus k times n. Clearly, m minus k is an integer, and that tells us that a is congruent to b mod n. Well, who cares about that? Well, if you look at the bullet point 2 that we just proved previous to this one, knowing that a is congruent to b mod n implies that bracket a n is equal to bracket b n, which is exactly what we were trying to prove. All right, so we've gotten through the first 3. We just have to make it through 4. Shouldn't be too bad. Once again, we're proving two sets are equal, that the union on the left-hand side is equal to the set of integers on the right-hand side, and we've got to approach it in the exact same way. We've got to prove the union of the sets is a subset of the integers, and that the integers, set of integers is a subset of the union of all those congruence classes. So every single congruence class contains only integers. It doesn't contain all the integers, but it doesn't contain anything that's not an integer. Which means that when you take the union of all those congruence classes, that only contains integers as well, which is exactly what it means for that union of congruence classes to be a subset of the integers. So that first one is actually pretty easy. The one that's going to be slightly challenging is going to prove the other inclusion. So for the other direction, remember, we're trying to prove that the set of integers is a subset of the union of those congruence classes. We're going to assume that x is an integer, and we're going to show that x is in the union of the congruence classes represented by 0 through n minus 1. Well, how are we going to do that? Well, there's something special about 0 through n minus 1. If you look at it the right, or in a certain way, you can think it's, well, that reminds us of the division algorithm, right? It could, like our remainders between 0 and n minus 1, which means we want to take that x and divide it by n, right? And then see what its remainders could be. So we're going to use the division algorithm, dividing x by n. So that gives us x equals qn plus r. Q is the quotient, r is the remainder. And by the division algorithm, we can make those q and r such that the remainder r is between 0 and n minus 1. But if we look at that closely, that just tells us that x and r is congruent to are congruent mod n, right? What does it mean for x to be congruent r mod n? Well, x has to be some integer times n plus r. And that integer times n would happen to be the quotient. Nice. So that says, since x is congruent to r mod n, that says x is in the congruence class represented by r. But remember, r is between 0 and n minus 1. That means x has to be, that congruence class represented by r has to be one of those congruence classes represented by 0 through n minus 1. That means if we take the union of all those congruence classes, since x is in one of them, we don't know which one, but it's one of those congruence classes represented by r, which is between 0 and n minus 1. That means x has to be in the union of the congruence classes represented by 0 through n minus 1. Which, by the way, is exactly what we wanted to prove, right? Since the subset inclusion goes in both directions, that says the union of those congruence classes is equal to the set of all integers. And that ends the proof. So I think you're ready to, I mean, you can continue working on the in-class activities if you didn't get through all of them, but you're welcome to move on to the next video that talks about binary operations.